and he was working alone there, and that's what happened. Even hours after he died, when the firefighters went in, they measured really high levels of xylene vapors in there. So there are a lot of problems with this job. One, it wasn't even marked as a confined space. There was no confined space program. The guy was in there working alone. There's sometimes a misconception that if you have a meter that's designated maybe to measure oxygen levels, which is very common, sometimes workers think that's going to sniff out any sort of hazard. And in this case, where xylene was the issue, that wouldn't have helped you. So that's something to really be aware of in construction. So how many of you guys get into doing air monitoring for some of your work? Okay, so what kind of things are you measuring? Okay. He said most of his industrial hygiene work is industry-based. Any other construction IH type folks? What kind of stuff do you... Hey, Scott! There's an old IH hand there, Scott Schneider. How about back here? What did you raise your hand? What kinds of stuff? Okay. So this is how we do it. You know, we have sampling pumps and devices to calibrate the pumps, and we're measuring exposure for a number of reasons, trying to figure out the degree of hazard, figure out how well the hazards are controlled, determine where the exposures are relative to some occupational exposure limit. And, you know, typically the limits are based on the concentration of the contaminant in the air, you know, contaminant concentration over volume of air. And so, for example, the hexchromium standard, which the gentleman back here said he does sampling for, the OSHA permissible exposure limit is 5 micrograms of hexchromium per cubic meter of air. Sometimes we do monitoring for diagnostic purposes, like for figuring out, like I said, the high exposure task. And this is some pictures here where we're actually measuring the airflow of this little local exhaust ventilation unit. So sometimes there's an issue of figuring out regulated work zones. You know, with the hexchromium standard, you're supposed to put up a little regulated area where only those workers who have been briefed and protected for hexchrome are allowed to enter. You might do diagnostic evaluation just to figure out the perimeters of those regulated work zones. So what we've done over the years when we do exposure assessment is that we involve workers in the process because they really know the work and they communicate well with other trades, and it kind of integrates the whole idea of health hazard control into the work, which is a positive thing. And we have something we call T-beam for task-based exposure assessment model, and this is something that we've used since the mid-90s and applied it primarily to welding fumes and silica. But the focus is always on trying to identify and evaluate an engineering control and to, like I said, have journeyman partner with hygienist. And so here on the left, we're sampling a painter for heavy metals and silica, and we're doing the quantitative measurements. But on the right, on that same job, we have a journeyman construction worker who's noting all the different variables like the configuration. Can't hear me? On the right, he's noting variables like the configuration of the containment and, you know, how many workers are in there and different things that can impact exposure. And that's the kind of information you really need to interpret your exposure data. So I won't spend a lot of time with this, but just in terms of visualizing, when we talk about air concentrations, and I mentioned that the hexchromium permissible exposure limit is 5 micrograms per cubic meter of air. To visualize how small a microgram is, keep in mind that a pack of sugar is 5 grams of sugar, and there's 1 million micrograms in every gram. So in that little pack of sugar, you've got 5 million micrograms of sugar. So to get 5 micrograms, you'd have to cut it into 1 million pieces, and the millionth of that little amount of sugar would generate, that would be 5 micrograms. And then a cubic meter is just a visual image of what that is. So that little bit of sugar and that volume of air would represent 5 micrograms a cubic meter. And yeah, that's important in part because sometimes we have controls in place and we'll see a huge reduction in the dust visually, and that's a good thing. But there's a very high probability or possibility that even though we're not seeing dust, there actually is still elevated exposures, but it's a concentration so small we can't see, but it's concentrations that are high enough to exceed the legal limit or potentially be harmful to that worker, which is why, again, we had to do the air monitoring. So when we're trying to evaluate whether there are overexposures, there's 3 different places that we generally go to for exposure limits, and one are the OSHA PELs, which are legally enforceable. The other is NIOSH recommended exposure levels, and then there's something called threshold limit values, which are a consensus-derived standard. And these actually tend to be more up-to-date because there's a process for updating them. So to just give you some practice in terms of how you would use an OEL, this is some welding fume data that we have for just total fume. And if you look at that middle column in kind of a purple color there, we see that the mean exposure in 95 was roughly 5.8, let's say 6 milligrams per cubic meter. And there's really not a welding fume PEL at this point, but there used to be one of 5 milligrams per cubic meter, and there's also a TLV of 3 milligrams per cubic meter. And the majority of welding fumes are small enough to be what we call respirable, that they can get deep down in the lung. So, you know, if we consider welding fumes respirable, then we might use that TLV of 3 milligrams per cubic meter. So if we're measuring exposures that have a mean of 6 milligrams per cubic meter, how many would say we have an overexposure? Only 2? How many would say we aren't exposed? How many don't care? So the answer, the first 2 or 3 of you are right, that there definitely would be an overexposure. And this is the same scenario for manganese, that we see exposures around 0.2, which is the equivalent of the current TLV. So in industrial hygiene, we talk about something called the hierarchy of controls, and what we're referring to there is that, you know, we actually rank which control is the best approach, and in terms of industrial health hazards or construction health hazards, the number 1 way to go is through engineering controls. And that could be like substituting materials out, say in the case of silica sand as an abrasive, if we switch to water blasting, say, instead of dry silica blasting, that would be a good substitution engineering control. Or if we implement ventilation. Administrative controls, that might be where, say, if it's not realistic, but let's say you've got a crew of laborers and you're on a milling job, and you want to minimize asphalt fume exposure, so you say to one group of laborers, okay, you guys work this in the morning, and then I'll have you doing something else in the afternoon, and another crew will come in just because it kind of reduces their exposure, but that's not very realistic for the most part. And then PPE would be respirators and that kind of thing. So that, although that's the way we want to go, just from a good science, health-based point of view, and the OSHA standards require you always use engineering controls first, they're still pretty rare in construction. But they're more effective. They not only reduce the exposure level, but they reduce the variability in exposure, which is a big problem in construction because we see real large variation. They're more comfortable for the worker. You got to remember that, well, for any control, there's training required on how to use it, and it requires some upfront planning. So ideally, if a client, a construction owner, puts into the job bid documents that the employer must have a local exhaust ventilation system or a lead safety and health control program that includes engineering controls, then we're more likely to see that contractor plan for that. Otherwise, it's not commonly used. And this is just a picture of a job I was on where this guy, between his welding hood, his fall protection, his chaps and respirator, he really couldn't wear a little sampling cassette. There was not enough room where he was working. So it gets to be burdensome when you have all this different equipment on you. And then there can be issues with communication. I remember as a carpenter many years ago, if you're on a scaffold and you're asking a guy down on the ground to give you a certain dimension of wood and you got a respirator on, it doesn't really work, so you wind up taking it off and hollering it down there. So just example of local exhaust ventilation. One thing we see is once we get the ventilation on the job, then there's the issue of placement. And on this job, we were doing a very controlled study, and so the the hygienist made sure that the hood was positioned exactly where it needed to be. But oftentimes you might see this kind of thing where the hood up there at the top is above the guy's head, so he's intercepting the fume in the hood. So the gentleman here mentioned asphalt fumes, which is a big issue for road work folks, and there was a project at NIOSH that was kind of a really good model of how we can attack health hazards in construction, and it was the asphalt paver agreement, and Scott could probably speak to this better than me because the laborers union were involved in this, but essentially the way I understood it, and when I first got involved, the issue was that NIOSH was coming out with a criteria document for asphalt that was going to document that asphalt was a carcinogen, and also there was some standards development process potentially too, and the asphalt industry was very concerned about this because they felt it would have an adverse effect on their business. And so they said, you know, look, rather than debate if it does or does not cause cancer, let's just figure out a way to control the problem. And so they entered into agreement with NIOSH and to labor unions, laborers, operating engineers, and NIOSH and other groups. And what they did was the paving industry put up the money for the equipment that NIOSH in turn independently evaluated for effectiveness in terms of engineering control for asphalt fumes. And the result was that for all new highway class asphalt pavers, they will now be equipped with this ventilation system that blows the fumes away from the worker. So that's kind of an overview of industrial hygiene and construction, and I'm just wondering, we already talked about where you see personal air monitoring. Has anyone ever seen an engineering control for a health hazard in place on a job? No one's seen anything. I told you it was rare, right? What? Water for cutting block. That's a good one. Like for a stationary saw or portable. But that's an example where in the bricklayers, for years they said they always use the stationary wet saw for cutting brick and block, and then productivity became such an issue that now the contractors didn't want them to come down from the scaffolds to use the stationary saw, so they were throwing a portable masonry saw up on the scaffold, and now they were getting exposed to enormous amounts of masonry dust from that particular, you know, tool and process. But that's an old school kind of good engineering control that would involve no change in how things were done historically. Anything else you've seen or you think would work? Okay. So I'm just going to go over one case study quickly, and this was done with the New Jersey Department of Transportation, and it evolved out of the recommendation from NIOSH that there be a ban on use of abrasive that had more than 1% crystalline silica in it, and this goes back to 1974. And as I showed you earlier, the abrasive blasting, the painters, in terms of silicosis, that is definitely probably the highest exposure task. And in most European countries, they don't allow sandblasting anymore. So, and in New Jersey, on DOT jobs, they don't allow it. For many years now, they've prohibited use of sand for health reasons, but also because of a hazardous waste disposal issue. So back in the 90s, NIOSH had done a study where they looked at alternative abrasives, and they looked at not only silica but metal hazards, because a lot of the substitute abrasives have metal hazards associated with them. And what they found was that this particular abrasive called specular hematite was the least hazardous. And it's like an iron oxide kind of product that's mined up in Canada. So what we did was we partnered with the New Jersey DOT, and we used the T-beam approach I mentioned earlier to try to actually test under field conditions 3 different substitutes for silica sand. And in 2002, we looked at specular hematite, 2003, coal slag, and then 2004 in steel grit, which is essentially what they use in New Jersey DOT projects at this point for the most part. And the contractor was the same throughout all 3 years, and all of the bridges were pretty much the same. They were pedestrian bridges, all built and painted about the same era, all early 1960s. You see a lot of, urban art there, the graffiti that they had to get off. And this was a typical setup for the job. This was all night work because of highway traffic issues, so that was interesting. But they would set up about 11 o'clock at night and blast for maybe till 2 in the morning, and then they'd have to break down and be off site by 6 a.m. or 5 a.m., or there were millions of dollars of fines if they weren't gone. And this was the containment setup they had, and they actually worked off that truck platform you see there. And this is the guy I showed you earlier in the containment area. So just to kind of review the health hazards that are associated with some of the abrasives are manganese. We see that in steel grit, and like I said, that's associated with neurological effects very similar to Parkinson's disease, chromium-6 nickel, and beryllium and arsenic. And when we compared the abrasives, what we found is that for all the abrasives, the silica level was below the NIOSH criteria of 0.1%, so they all were considered silica-free by that definition. But unfortunately, the silica levels were all still high because there was silica in the paint. And when you're blasting at these high, 100 PSIs, you're going to generate enormous amounts of dust. So if you have 10% silica in the paint, you're going to have very high silica levels. For the coal slag, we also saw elevated levels of arsenic and beryllium. And for the steel grit, we saw elevated levels of cadmium, chromium, nickel, and manganese. And for all of these, lead was an issue because there was lead paint, but that's a given. So in general, what we found was that all of the abrasives resulted in lower silica exposure than you'd expect if they were using silica sand. But unfortunately, there were other hazards associated with the substitutes, like the beryllium and manganese. And what we learned was that, and what we were kind of surprised about, was that the paint was such an important source of silica exposure itself. We knew paint was an important source of exposure for lead and heavy metals, but also for silica. But given this, the specular hematite did perform the best of the three. And you can't have a presentation of the Keystone State without at least one reference to Ben Franklin, and hopefully there's more Flyers fans than Blackhawk fans in the room, right? So I figured I'd end on this note. So I'm a little bit early, but does anyone have any questions or comments? Yeah, it might be helpful. If you don't mind standing up, it might be easier for them to hear you. With the hearing loss, and Scott might want to add to this too, that there's not, there's hearing aids, but it's not going to come back. It's not going to get any better. With regard to silica, there's, can you hear me? Oh, I'm sorry. The question was with regard to health effects from silica, from hearing, and from noise. What was the other one? Lead in general. How, is it permanent, or can it repair itself after exposure ceases, correct? Is that kind of the question? So for noise, the answer is no, it doesn't get better. If you remove yourself from noise, it's not going to get worse maybe, but it's not going to get better. For silica, some people develop illness, some don't. There's something called, I think it's progressive accelerated silicosis, where for some people, even after they are removed from exposure, the condition continues to deteriorate. For others, it just sort of remains, it doesn't get any worse. So in the case of silica, you could have some effect, but not enough to be disabling, or you could have an effect that was disabling from that initial exposure, or you could, have an exposure that was so bad that there was progressive damage even after you removed from exposure. For lead, I'm not a doctor, so that would be better one for a doctor to address, but what I've been told is that you can have some permanent kidney damage and neurological effects and reproductive effects and so on, but if you get that person, if you catch the elevated blood lead early, remove them from exposure and get the get a lead safety and health program in place, then the chances of that happening are far lower, right? So, you know, someone who's a painter and is consistently carrying very high blood lead levels, that person's probably at pretty serious risk of long-term chronic illness. But hopefully for short-term kind of things where we can remove them from exposure, that may not be the case. Is that? Did you want to add anything, Scott, to the question about? Okay. Anybody else have a good question like that? Why don't you stand if you don't mind? It is here. It's easier to hear. So the question was, in the case of silica where you see an overexposure or an exposure that you have some level of concern about, and this is in highway work where the source of exposure can vary, is there some type of protocol you would follow? And I guess what you kind of would have to do is do sort of a hazard analysis before the job starts to figure out what those tasks are and build in the controls. So say in the case of jackhammers, there's been some research done that shows use of water supplied to jackhammers is a pretty effective way to control the problem. But and there's actually a website that shows you how you can build the that control, and the laborers, Ken Hoffner with the Laborers Union was responsible for that, and Alan Echt at NIOSH has done a lot of work with that. So if you want me to put you in touch with people, it would be great resource. I'd love to do that. But I don't think there's like a one-size-fits-all thing. You know, typically it's going to be local exhaust ventilation, water, or, you know, reducing the amount of time you're using that piece of equipment. But you kind of have to design it for each piece of equipment and each particular task. It's a good question. I'm glad you asked it, because that's really the key, is that you anticipate what the problem's going to be and build in the control at the onset. Because as you all know, once the job's underway, it's over before you know it, and it's too late. So these are good questions. Anyone else got a good one? Or it doesn't even have to be a good one, just a question. Nothing? No one else? There's one. Yeah, well, you know, that's a good question. The question was, if a guy, like in the case of the painting, he's wearing a supplied air respirator, blasting helmet, is he still overexposed? And that's where it gets into what the levels are, right? And that, in that case, I believe it was lead. The lead levels were so high at one point, even with the 1,000-fold protection factor of the blasting hood, he would have been overexposed. Now, they still will wear a negative APR underneath that, but I don't think that really adds to the protection factor at that point. So sometimes it does, and sometimes it may not, you know. And again, that's why, you know, what we find often at this stage, unfortunately, is that, say in the case of masonry cutting, or if someone's doing that continuously 8 hours a day, a lot of the technologies that are available are effective at reducing exposure maybe tenfold, but not effective enough to get them below that REL. So for a lot of tasks like that, you're going to have to use the engineering control and a respirator until you can kind of get the engineering control up to speed. But reliance on respirator alone, you raise a good point or a good question, and it just from a protection point of view, it may not be adequate. And that's why you have to know what the exposure levels are, and you have to know what the protection factor of that respirator is. And if, you know, say it's 1,000 assigned protection factor and you're seeing lead 10,000 times the PEL, that's not going to be enough, right? So these are all good questions. They make for a more interesting presentation. You're bringing up good things I didn't cover.